Hello and welcome to Physics with Amol sir. So this video is for class 12 and we are going to continue with the chapter of current electricity. In the previous video we talked about the concept of drift velocity and the relation between drift velocity and electric current. Okay, today we are going to discuss mobility and we will talk about the temperature dependence of resistivity. Okay, so let's begin. First let us talk about mobility. Mobility we define as the magnitude of drift velocity per unit electric field. So here is the formula: mu is equal to Vd upon E. Mu is the symbol for mobility. Okay, and you can see the SI unit for mobility will be meter square per volt second. Okay, so that is the concept of mobility. I am sure it is very easy to understand, so I am not going to explain it further. Then of course you can substitute the expression for Vd and this will be the formula that you get for mu. Okay, that I will be leaving as an assignment for you. Next we will talk about the concept of temperature dependence of resistivity. Okay, so we have previously discussed that the resistance of a material will depend upon the length and the area of cross section, provided that the temperature and everything is constant. Okay, but if you go on changing the temperature, then that also affects the resistance and in turn the resistivity. Okay, so that is what the concept is about. As the temperature changes, the resistivity also gets affected, and this is the concept. Okay, so now let us find a relation for the temperature dependence of resistivity. For that we are going to use a knowledge that we have. What is the knowledge? The knowledge is that fractional change in resistivity is directly proportional to the change in temperature. Okay, I know many words. Let us see what is the meaning. Now what is meaning of fractional change in resistivity? Let us say that at a temperature, let us say 0, some kind of 0, it can be 0 Kelvin or 0 degree Celsius. At 0 degree Celsius or 0 Kelvin, the resistivity for a given material is given by rho naught. Okay, so that will be our initial resistivity. We change the temperature from 0 to some T Kelvin. Okay, when the temperature goes to T Kelvin, now the resistivity changes and it has become rho T. Fine, that is easily understood. So earlier we had a resistivity of rho naught. Now the resistivity has become rho T. What will be the fractional change in resistivity? Fractional change in the resistivity will be the change in resistivity divided by the original resistivity. What is change in resistivity? Rho T minus rho naught and divided by the original resistivity rho naught. Okay, and as I said, this will be directly proportional to delta T, that is change in the temperature, that is T minus T naught. Okay, whatever was the initial temperature. So we get rho T minus rho naught upon rho naught directly proportional to delta T. Okay, then as usual we can remove the sign of proportionality and we put a constant. So we will get rho T minus rho naught by rho naught equal to the constant we put here is called as alpha delta T. So alpha is called as the temperature coefficient of resistivity. Okay, and as you can see it is a constant. You can write the formula like this. Okay, to get a formula for alpha, so we get alpha equal to rho T minus rho naught upon rho naught into delta T. And how will you define alpha? You can define alpha, that is temperature coefficient of resistivity, as the ratio of fractional change in resistivity to the change in temperature. The SI unit for alpha will be Kelvin inverse. Why Kelvin inverse? Rho T minus rho naught, this will have the SI unit of resistivity divided by resistivity, so no unit. Okay, so 1 by delta T, that will be the unit, so 1 by Kelvin. Okay, so per Kelvin, that is the SI unit for alpha. We can also write this formula as alpha equal to RT minus R naught upon R naught delta T. What is RT? Resistance at temperature T minus R naught, resistance at the initial temperature 0 divided by R naught into delta T. both these formulae will give you the value of alpha. Okay. Now in the textbook there are two solved examples, example number 3.3 and example number 3.4. So I want you to solve those. If there are doubts, we will be asking. Based on these formulae, you will be able to solve very simple questions, but in exam these questions will be asked. So I hope you understood the formula, but then what is the meaning, let us see. Let us take the example of copper for example. Okay. So we will make a graph for copper. This will show the resistivity on the y-axis and temperature on the x-axis. So as we go on increasing the temperature, what we will notice is that the resistivity will also go on increasing. Okay. So you get a graph something like this. Okay. Here is the proper diagram from the textbook. You can see with the values also. So as you notice, as the temperature increases, the resistivity goes on increasing. Okay, so this happens in the case of many conductors. At high temperatures, you can see for some conductors, it will actually be a straight line. For example, in the case of nichrome, in the case of platinum, okay, the graph of resistivity versus temperature is a very nice straight line. Okay, here are the diagrams. Okay, these are the graphs of resistivity versus temperature. And this relation helps us to understand the temperature dependence. Okay, so for these kind of conductors, we will see as the temperature is increasing, the resistivity is also increasing. So for conductors, as the temperature rises, the resistivity also rises. But there are some materials which are called as semiconductors, which again in some later topics, later chapters, we will be discussing them in more detail. Okay. In semiconductors, the opposite thing happens. What happens in semiconductors? As temperature rises, the resistivity actually decreases. So for semiconductors, you notice a graph like this. Okay. So in exam, you might be asked, a graph will be shown of resistivity versus temperature, and you can identify if it is a positive graph, if it is an increasing graph. In that case, you will know it is a graph for a conductor. If it is a graph that is decreasing, in that case you will see it is a graph for a semiconductor. I said there are some materials for which the graph of rho versus T is actually a straight line. Okay, one of those materials is platinum. So what we do, we actually use platinum for making something called as platinum resistance thermometers. Okay, here is the photograph. So how we use it, basically for platinum we can actually plot that for a certain temperature how much will be the resistivity. Okay, we can actually have a graph for platinum in this case. So what we do, we make a thermometer using a strip of platinum. So if it gives a certain amount of resistivity, we can backtrack and say at that it must be having a certain temperature. So industry uses for measuring very high temperatures, we can actually use this platinum resistance thermometer. Okay, so this is one of the applications of this particular concept. Next, let us talk about some of the limitations of Ohm's law. Ohm's law, as we know, it states that for given resistance, V is directly proportional to I. But then there are some cases where the Ohm's law does not get followed. Okay, for extreme high voltages, extreme high currents, we notice that V does not remain proportional to I. This is one of the limitations. The second limitation occurs when we change the sign of V. Okay, if we change the polarity, in that case we see that the relation does not keep track. That is, V does not remain proportional to I. This happens mostly in the case of semiconductors, as you can see in this graph here. Okay, and a third limitation of Ohm's law happens in a material like GaAs, gallium arsenide. In gallium arsenide, we get two values of voltages for the same value of current. Okay, so these are some of the cases where Ohm's law does not get followed. In fact, there is a large variety of materials which do not follow Ohm's law. Okay, as I said, semiconductors are one of them, and because of this non-following of Ohm's law, we are actually able to make a lot of use for them. Okay, in later chapters we are going to see that in more detail. Next, we will talk about the concept of electrical power. Power, I am sure you remember, power is defined as rate of doing work. Okay, in case of the electrical part, electrical power we define as rate at which electrical energy is consumed. Okay, so we can write the formula for power, P as W by T. W, that is, if you remember, you already have this formula. V is equal to W upon Q. So you can write W as Q into V. So you will get P is equal to V into Q upon T, and then you know that Q by T is nothing but electrical current. So power you can get as V into I. So this is how we define electrical power. So electrical power can be written as product of voltage into electric current. SI unit of power is again watts. Okay, same as what we had in mechanics. Okay, so this is the concept of electrical power. So these are the three ways that you can write power. Power you can write as V into I using Ohm's law. You can write V is equal to IR, so it becomes I square into R. Okay, or you can write it as V square by R. All the three equations, they give the derivation, the equation for power. So I hope all the concepts of today were understood. So these are all definitions. From exam point of view, 1 mark definitions could be asked, or based on this formula 2 mark numericals could be asked. Now these are of very simple nature. Okay, I hope that you will be able to solve them properly. So go through the solved examples that I told you, 3.3 and 3.4. Solve them in your notebooks. Okay. In the next class, I will be sharing some unsolved numericals for this. Okay. So make sure you are practicing all those. Now even after this, if there are any doubts, make sure that you are asking. In the next class I will try to solve them. Okay. Thank you.